So let's discuss a complex numbers being an analytic functions. A function, f of c, is analytic in an open set of complex plane values if f prime of c exists everywhere in the same complex plane values. Let's say we have all the set of values in the complex plane. If we choose f of c anywhere in that complex plane values, the f prime of z should also exist everywhere in that set. Now, a function f of c is analytic in C sub O if f prime of c is differentiable in an open set containing C sub O and its neighborhood. Let's say we choose C sub O as a point inside the complex plane values. All the points inside the circle is the neighborhood of the point C sub O. Therefore, f of c should be differentiable at that point C sub O and its neighborhood. Let us compare the real valued function derivative with the complex value derivative so that we can have some insights. Here is the definition of real valued function derivative. Suppose we are given a function f of x and we want to approximate the value at some point x. Then we will have a good approximation if we can move any point from x towards the chosen point, let's say x sub O, or we can define it as limit of delta x tends to 0. In this example, we can have a limit of x coming from left or right approaching x sub O. So let us see the complex valued function derivative definition. In this case, we will have an input in the form of complex number with term x and y, so that our output will be a complex number as well with term u and v. Let us see how the approximation goes with complex valued function. If we choose a point say sub O, we can have a limit approaching from our imaginary axis iv from bottom and top. We can also have a limit defined from real axis coming from left to right. Actually, if you can see, we can have a limit coming from any direction in the neighborhood of C sub O. We can say that complex number derivative is a little bit tricky, and it is not as straightforward like in the real number derivative. For us to have a systematic approach in defining our f of c, if it is analytic or not, here are the criteria that we should meet. First, it will satisfy the Cauchy-Riemann equations. Given a partial derivative of u with respect to x should be equal to a partial derivative of b with respect to y, as well as partial derivative of u with respect to y is equal to the negative partial derivative of b with respect to x. Next is, it is a continuous and differentiable at say sub O. Next is, it should have a power series. Let's take a look of a complex numbers derivatives and take a couple of examples and see if the limits are conforming to each other, and we can say it is differentiable or analytic function. Again, showing you the definition of the derivative on a real valued function and on the complex valued function. Let's do an example. Evaluate the derivative of f of c equals to c squared. So applying the formula, we will have a limit as delta c tends to 0 of c squared plus 2c delta z plus a c squared minus c squared all over the delta c. In this case, we will have limit of delta c tends to 0 of 2c plus delta c. Taking the limit, we will have our final answer equals to 2z. In this example, the limit is 2z. You may recall, this is the same as taking the f of x dx squared over dx equals to 2x of the real numbers. Given f of c equals to z bar, show that the limit f prime of 0 does not converge. So as we all know, z bar is the conjugate of our z that is equal to x minus iy. Applying our limit formula, we will have delta c tends to 0 of the delta c bar over delta c. And it is equal to delta x minus delta iy all over delta x plus delta iy. Here, we use delta c equals to delta x plus delta iy. Now, if our delta c is tending to 0, means both delta x and delta iy have to go to 0. If we let delta c go to 0 along the x-axis, then delta x goes to 0. Therefore, our f prime of c bar is equal to the limit delta c tends to 0, delta x over delta x equal to 1. Now, if we let our delta c go to 0 along the y-axis, then delta y goes to 0. Therefore, our f prime of c bar will be equal to the limit delta c tends to 0 of minus delta iy at the numerator divided by delta iy will be equal to negative 1. You will see that the limits don't agree. The problem is that the limit depends on how delta c approaches 0. If we came from other directions, we'd get the other values. Therefore, if we have limits that don't agree, f of c equals to c bar does not converge at f prime of 0. So let's go to complex number, defining Cauchy-Riemann equations and how we can use it in defining if our function is analytic or not. In theorem, if f of z is equals to u as a function of x and y plus ib as a function of x and y is differentiable at point say sub o equal to x sub o plus iy sub o, then the Cauchy-Riemann equation hold also at say sub o equals to x sub o plus iy sub o. Again, showing you the definition of Cauchy-Riemann equations. Here are the two equalities that we should meet for us to say that our function is analytic. I have here 5 examples that we can evaluate using Cauchy-Riemann equations to determine if the function is complex differentiable. First is f of c equals to c. We know that c is equals to x plus iy. Then, taking the partial derivative of u with respect to x, it will be equal to 1. And taking the partial derivative of v with respect to y is also equal to 1. So it satisfies the first equalities of Cauchy-Riemann equations. Let us take the second equalities. Taking the partial derivative of u with respect to y in our given equation will be equivalent to 0. And taking the partial derivative of b with respect to x is also 0. Therefore, we are meeting the second equalities of the Cauchy-Riemann equations. Of course, the negative sign in here will not matter because we have a 0. The function, therefore, equals to c is a complex differentiable. Taking the derivative of our function is just equal to 1. Next example, f of c equals to say bar. We knew that say bar is equals to x minus iy. So performing the equalities of Cauchy-Riemann equation, the first equality, taking the derivative of u with respect to x, that is equal to 1. And then taking the derivative of b with respect to y is equal to negative 1. In this case, we did not meet at least the first Cauchy-Riemann equations, and the function c bar is not complex differentiable. Next example is f of c given e to the c. And as we all know, e to the c is equivalent to e to the x plus iy, so that we can separate the e to the x constant value and have our e to the iy, for which our e to the iy, as we all know, is cosine y plus I sine theta y. So therefore, we will have equation e to the x times the quantity cosine y plus I sine y. Okay, first equality from the Cauchy-Riemann, taking the partial derivative of u with respect to x, that will be equal to e to the x cosine y. And partial derivative of b with respect to y, that is equivalent also to e to the x cosine y. Therefore, we met the first equality of the Cauchy-Riemann equations. Now, let us take a look on the partial derivative of u with respect to y, and that would be equal to negative e to the x sine y. Taking the partial derivative of b with respect to x, that is equivalent to e to the x sine y. Therefore, we also met the second equality of the Cauchy-Riemann equations. And it means the function e to the x is a complex differentiable. Taking its derivative, the derivative of e to the c is just the function itself. Next example, f to the c is given say plus say bar equal to x plus iy plus quantity x minus iy. So their sum will be 2x. Taking the partial derivative of u with respect to x, that would be equal to 2. And partial derivative of b with respect to y is equal to 0. Therefore, the function say plus say bar is not complex differentiable as we did not met the Cauchy-Riemann equation. Let us try f of c given 3x plus ix y to the cube. As you can see, this is in the form u as a function of x, y, and ib as a function of x, y as well. So we can directly apply the partial derivative. Taking partial derivative of u with respect to x, that would be equal to 3. Partial derivative of b with respect to y is equal to 3x y squared. So in this case, the first equalities of the Cauchy-Riemann equation can still hold with value of x equal to 1 and y equal to plus minus 1. Since there are points in x and y that the Cauchy-Riemann equation still holds, so let us check the second equality. Checking the partial derivative of u with respect to y equal to 0 and partial derivative of b with respect to x is equal to y cubed. So, for this equation to hold, the y should be equal to 0. And on the first equality, there should be no 0 at y because it will violate the first inequality. So therefore, the function 3x plus ix y to the cube is not complex differentiable. So that would be all for the definition of the complex numbers being analytic function, how we can perform its derivative, and how we can use Cauchy-Riemann equations to determine if functions are complex differentiable or analytic function.